Greetings, my name is Mike Levis and I'm an instructor with the Mountain Hood Ski Patrol Avalanche program. In previous discussions, we've covered the avalanche triangle and discussed the parameters that influence avalanche risk: weather, snowpack, and terrain. In this module, we'll tie all our previous discussion together and discuss what causes an avalanche to occur, namely the trigger. We'll start with a review of some of the factors that can strengthen or weaken the snowpack. We'll then talk about stress points that can increase the potential for a trigger to cause a release. We'll wind up with a discussion of triggers and avalanche releases. Let's start with a brief review of conditions that make the snowpack stronger. As we discussed previously, one of the key factors is temperature gradient in the snowpack. Low temperature gradient results in rounded grains that can easily be bonded together during melt-freeze cycles or during settling. On Mount Hood, we typically will have thick snowpacks and temperatures not far below freezing, resulting in low temperature gradient and a relatively stable snowpack. We typically do not have persistent weak buried layers. Our main cause of instability is rapid loading, either from snow or wind loading. As we mentioned in previous modules, time is a big factor in snowpack stability. After snow falls, gravity works to compact the snowpack, increasing the density and strength. During the settlement period, the snow crystals will slowly change, becoming more rounded and bonding together through a process of sintering. Conversely, factors that will make the snowpack less stable are high temperature gradient, resulting in faceted snow crystals that do not bond well together. High temperature gradients will occur with relatively thin snowpacks and air temperatures well below freezing. When coupled with long cold periods, these faceted snow crystals will form persistent weak layers that are not subject to the stabilizing influence of melt-freeze cycles. There are other factors as well that will contribute to weaknesses in the snowpack. We've talked about buried facets and buried surface hoar extensively. The nature of these snow crystal forms makes for very poor bonding between grains. However, as indicated in the last two bullet items, any difference in grain type or grain size between layers will impede the ability of the grains to bond and stabilize. The greater the difference, for example, the difference in grain size between layers, the weaker the bonding will be between layers. The picture on this slide shows a consolidated slab over depth hoar in a snow pit. This is exactly the structure that could result in a slab avalanche on a slope with slope angle greater than 30 degrees. And we'll cover a lot more of this during the module on snow stability testing. I want also to touch briefly on rime ice. This is a common phenomenon on Mount Hood. Rime ice forms when supercooled water particles freeze on the surfaces. The ice mass grows as more and more particles are added. Note that the ice mass grows into the wind. Rime ice can act as a weak layer for subsequent consolidated slabs. It also tends to form in cold conditions similar to that required for surface hoar. Note the picture on the right are rime ice particles forming on an individual snow crystal taken with an electron microscope. Very cool. So the avalanche triangle helps us identify the parameters that will determine avalanche susceptibility. Factors that will increase or decrease avalanche risk: slope greater than 35 degrees, unstable snowpack with a consolidated layer over weak layer, and lots of new snow contributing to rapid loading. But there's one more factor that's needed to convert the risk of an avalanche to a real avalanche. That's a trigger that can initiate avalanche release. So what exactly is a trigger? A trigger is any event that will increase stress on the snowpack to the point where the shear stress in the weak layer overcomes the shear strength in the bonds between snow crystals in the weak layer. Once the weak layer fails, there'll be a rapid increase in tensile stress that will cause a fracture in the snowpack at points of high stress. These fractures will release the slab to slide down the slope and the avalanche is formed. Please note that there's always some degree of shear stress in the snowpack from gravity. It's present all the time and is proportional to the slope angle. so steeper slopes will have greater shear stress due to gravity. This background level of shear stress is opposed by friction between the bed surface and the slab. So shear stress trying to pull the slab down the hill, gravity between the slab and the bed surface resisting the force of gravity trying to keep the slab in place. A trigger rapidly increases the shear stress to overcome friction and bonds between ice grains in the weak layer to initiate a release. Two important topics related to shear stress are creep and glide. Both are a result of the force of gravity acting on the snowpack. Glide is the uniform motion of the entire snowpack sliding down the slope face under the force of gravity. You can see that in the center portion of the drawing here. Creep is the effect of both gravity and friction on the snowpack. The force of friction acts to oppose the force of gravity at the interface between the slab and the bed surface. The net effect of this is that the force on the snowpack, friction plus gravity, is greater at the surface of the snowpack than at the bed surface interface, as shown in the leftmost image. This results in a non-uniform stress across the snowpack, as illustrated in the rightmost image. The effect of creep and glide can be seen in this graphic. Here we have a slab over a weak layer over a buried slab. The buried slab acts as the bed surface. The non-uniform stresses produced by creep and glide deform the weak layer and increase shear stress across the weak layer. This increased stress on the weak layer may be enough to initiate a release over time, or it may reduce the amount of external stress that would need to be added by a trigger to initiate a release. As we discussed in the module on terrain, the slope of the terrain can increase stress on buried weak layers at localized points. As mentioned previously, terrain convexity creates tension that weakens the snowpack, and terrain concavity creates the compression that increases snowpack stability. Complex features in the snowpack act as stress magnifiers by increasing tensile strength that can lead to fractures. The red circles on this slide show points of increased stress due to features of the terrain. This increased stress can lead to fractures during buried layer collapse. Fractures can propagate from weak point to weak point, creating the crown of an avalanche. So to summarize, stress concentration points such as trees, rocks, sunlines, and snow pillows can be points of fracture. Fractures can propagate between weak points, leading to crown formation and slab release. Try and visualize this when assessing a slope for avalanche risk. Where are potential weak points? What would happen if a fracture at one weak point propagated to another weak point? How much of the slope would slide? It's important to remember that the slope is not uniform. Local points of non-uniformity can be local points of stress or weakness that will be the first places to fail. For example, we know that steeper slopes have higher shear stress. Therefore, local points that are steeper than the average slope angle, such as a rollover point, will experience more stress. Wind loading on the lee side of a ridge will create increased stress on the snowpack. Sheltered spots with thinner snowpack will have a greater likelihood of facetted snow due to larger temperature gradients in the snowpack. This could lead to a buried weak layer and reduce snowpack stability at that point. So don't make the mistake of assuming that the slope you're looking at is a uniform canvas of snow. It's more like a mosaic of topology with different levels of stress and different likelihood of failure. So let's move on and talk more specifically about different kinds of triggers. Let's start by discussing some natural triggers. Slab avalanches can be triggered by a variety of means: rapid loading due to heavy snow, wind loading, or even seismic events. To initiate a release, we must first have the ingredients for a slab: a cohesive layer over a weak layer. The trigger adds stress to the snowpack, causing weak layer collapse. Weak layer collapse increases tensile strength, leading to a fracture at weak points in the snowpack. Fracture propagates to form the crown and flanks, and the slab is released. The arrows in the photo show the crown line. You can see where there are buried structures in the crown line that acted as fracture points. The fracture propagated between these weak points. So you can see in the slide on the leftmost arrow, it's pointing to what looks like a rock wall. And the center arrow points to what looks like a buried rock structure of some kind. And the rightmost arrow points to what looks like another buried rock structure of some kind. And you can see that somewhere along here, probably at the rock wall where it looks like the slope is the steepest, a fracture occurred and it propagated across from one weak point to another. And that's what formed the crown on this avalanche. So when we talked previously about looking at the slope, identifying where fracture points might be, and visualizing what happens if a failure at one of those fracture points connected with the other fracture points, that'll give you an idea of potential location of an avalanche, and you can then assess the risk accordingly. A loose snow avalanche has a different release mechanism. Since there is not a cohesive layer, release occurs when the slope angle exceeds the angle of repose and gravity overcomes friction. Release occurs at a specific point and proceeds to gather adjacent snow as the slide progresses. The release has a teardrop shape as it expands down the slope. Cornice failures can act as triggers. When cornices fail, they will release very large boulders of snow and ice that impact downslope. The impact can trigger a slab avalanche. Cornices can fail for a variety of reasons. Natural release occurs when the weight of the snow in the cornice causes a release. Man-made releases can occur due to bombing or weighting by a skier or snowmobiler. So triggers can be anything that rapidly increases loading on the snowpack. They can be man-made or natural. Rain rapidly increases loading without increasing strength, so rain can act as a trigger. Heavy snowfall or heavy wind loading events rapidly increase loading. However, in most man-made avalanches, the trigger was the person who actually ended up being caught in the avalanche. This graphic is an example of a natural trigger. Wind loading creates a cornice and loads the leeward slope. A cornice releases, landing on the slope below, triggering a slab avalanche. This next slide shows a man-made avalanche. A skier triggers a slide, luckily for the skier, at the top of the slope. In this case, the skier appears to be above the fracture point of the crown, so hopefully he or she was not carried down the slope. In this case, the weight of the skier caused enough additional stress on the snowpack to cause the failure of a weak layer and a fracture releasing the slide. Note that the fracture appears to be at the point of convexity of the slope. So it looks like there's a slight rolling of the slope right there, and a point of convexity that would have slightly increased stresses. And you can see that the consolidated layer is quite thick. So that may be where the fracture point occurred due to the additional stresses because of the convexity of the slope, and then the weight of the skier alone was enough to cause the slide. This slide shows another example of man-made trigger, in this case as part of avalanche mitigation efforts at a ski resort. So we've discussed the mechanics of avalanche release. Remember, to have a slide, you need to have a consolidated layer over a weak layer on a slope steep enough to slide. A trigger is then needed to initiate a release. A trigger causes a release when the shear force exceeds shear strength in the weak layer. Weak layer collapse increases tensile strength at weak points, leading to a fracture and slab release. Note the photo on the left. You can see a consolidated layer over a weak buried layer in the snow pit. The trigger in this case might just be the weight of the snowmobiler adding stress to the snowpack. And that concludes this module. So our next module will be on snow stability testing. I look forward to seeing you all there.